thanks to Les for inviting me. I met Les at ASPW, Advanced Space Propulsion Workshop. I think it was last year in Colorado Springs, and I've been involved in the interstellar field for about a decade now. I did my master's degree thesis on exotic propulsion. That's when I first got exposed to Mark Willis's Breakthrough Propulsion Program, for example. First got interested in the work of Miguel Alcubierre and his stuff on warp theory and other such stuff. And met Claudio in 2001 at the first field propulsion conference in Brighton. And so I've been sort of involved in the field, like I said, for about a decade now. And you know, the last few months have been a very exciting era, I think, for everyone involved in interstellar research. I mean, the DARPA 100-year Starship, which I think we all heard about, has really galvanized the interstellar community and created this buzz of activity. And so obviously this is $500,000 of seed funding, which they're offering for an organization not to build a starship, but to create the machinery, to create an organization that will be able to stand the test of time, to create a multi-generational, pan-decadal company. Now, one thing to keep in mind is that the average lifespan of a company in the United States is about 30 years. And so what DARPA want to do is seed fund an organization that could last 100 years, which is about the amount of time that we're estimating. It's going to take us to develop, go through that technology roadmap, increase the technology readiness levels of certain technologies that we're interested in today, fission propulsion, fusion propulsion, beamed energy propulsion, and so forth. And so another thing that they really want to do is, once they've given this money away, they want to move away from government funding. We have very capricious programs start, programs stopped, Congress doesn't like something, and what they want to do is sort of really give this over to the next Google or to the next Apple. I mean, I don't know if any of you saw in the news recently, but Apple had more spending money available to it at one point than the US government. It had sort of $74 billion sitting there. So, the aim of this $500,000 is to seed fund an organization that's perhaps going to be that next Google or Apple, but it's going to divert resources to funding people like you and I who are interested in manifesting that dream of interstellar propulsion. And so I've been privileged for the last couple of years to be involved in a project called Project Icarus, and more recently we founded a non-profit foundation, Icarus Interstellar. And so I'm going to be talking a little bit about that today. So really the structure of my talk, and this is a perturbation of a talk that I did give in Orlando last month, and more recently with Al Jackson, who invited me to the AIAA Lunch and Learn workshop last week, I think it was, in Houston. And so I'm going to say a few words about the physics of interstellar travel. Why is this such a challenging problem? I mean, we've sent human beings to the moon. Well, it's a very difficult problem, so I'm going to try and articulate that. Then I'm going to go into the details of Project Icarus, what it is we're working on, and what the non-profit foundation is sort of focused towards. And then, if there's time, then I'll say a few words about specific Starship designs. There have been a few detailed studies in the past. We had a little bit from Les today, for example, about Project Orion and Project Daedalus, and so we'll go into a little bit of the technical details of those projects. So let's talk about just the enormity of this problem. As was mentioned earlier, back in the late 70s, 1977, the Voyager probes were launched. And they are to date the farthest and fastest spacecraft that humanity has ever launched. Traveling at 38,000 miles an hour, Voyager 1 is 116 astronomical units from Earth. Les gave a beautiful example of turning things into feet. What I'm going to do is give an example in terms of the United States. And let's say that we shrink the scale down and we locate Earth in New York City, and we locate Alpha Centauri, 4.3 light years away, over in Los Angeles. Well, where is Voyager currently on its trip from New York to Los Angeles? It's traveled just a single mile in that trans-American trip. So it's taken 34 years just to travel a single mile in that 2,500 or so mile trip. And so obviously it's a problem of distance. And what we want to do is travel much faster to get there. As Les alluded to, it's going to take on the order of 50, 75,000 years, I think it is. And what we really want to do is increase the velocity by a factor of about 1,000, so we can reduce the travel time, to be consistent with timescales of a human lifespan. You know, we would like to see the fruits of our labor. We would like to send a probe and see it reach its destination and receive that information. You know, this isn't something for our great to the nth degree grandchildren. We want to see the fruits of our labor. So that's really what we sort of want to focus on. Now, the challenge becomes more apparent if we consider one of the most elementary equations of rocket science, the Tsiolkovsky rocket equation. And it relates the payload, the fuel to mass, the mass ratio of the fuel to the structure on the left-hand side, which are denoted by R, to how fast you want to travel, or more specifically the delta V, and to the specific impulse of the fuel that you're using. Now, if you want to travel to, say, Alpha Centauri in about timescale of human lifespan, you need to be traveling at about 10% the speed of light. And so when you plug in 3 times 10 to the 7 into the delta V, which is 10% the speed of light, and you stick in the value for the specific impulse of a traditional chemical rocket fuel, it's about 460 or so seconds for the space shuttle fuel, what you get is that you need more rocket fuel mass than there exists mass in the entire universe. I think that's an absolutely remarkable result, but what it demonstrates is that a single-stage chemical-propelled rocket engine is never going to reach the closest star on timescales of a human lifetime. It's a physical impossibility. And so we have problems and challenges that we need to overcome. Fortunately, chemical rockets aren't the only way to go. I mean, we're a clever species. You know, we understand physics, and what we've started to, really appreciate roughly, last century or so, is that rather than extract energy from the creation or destruction of chemical bonds, which is how we liberate energy for chemical propulsion, that if we journey into the nucleus of the atom and we move into the field of fission, where we sort of, rip the nucleus of a high atomic number particle apart, or fusion, where we fuse together light elements, we see that there's far more energy that we can liberate. And so this really table sort of put things into perspective. So, what we have here is the type of reaction, and what the maximum amount of energy we can extract, we believe we can extract from that reaction. So for chemical energy, 1 kilogram, you can typically extract about 15 million joules of energy. But when we make the jump from chemical to fission, you see that we go up by a factor of about 1 million. So for a single kilogram, we get about 1 million times more bang for our buck. For fusion, that's a 10-fold increase on fission. And so, we get 10 million times more energy than we do from chemical energy. And then antimatter, which was alluded to earlier, that is when particles and antiparticles meet and annihilate each other perfectly, according to Einstein's E equals mc squared, we get 9 times 10 to the 16 joules of energy per kilogram. So we know that there are techniques out there that we don't need, for example, warp drives or wormholes, that there is known physics that will allow us to liberate far more energy and perhaps one day be utilized for propulsion. So let me tell you now a little bit about Project Icarus. So it's, and I need to tell you a little about the name as well. So sometimes people say, well, why are you calling it Icarus? Wasn't he the guy who flew too close to the sun and his wax wings melted and he died, and it's an expression of human hubris? But what we like to think, well, first off, it's the successor of Project Daedalus, and Icarus was the son of Daedalus, so we want some consistency with the name there. And also we like to think of Icarus as a pioneer, someone who pushed the machines of his day to their limits, and in doing so, revealed their hidden faults and allowed engineers and creators of the future to build bigger and faster machines. So Project Icarus was inspired by Project Daedalus, which ran from 1973 to 1978, which was conducted by the British Interplanetary Society, which was, at the time, probably the most detailed interstellar starship study that was ever done. And it was a volunteer study, which is what Project Icarus as well. So our team, we've got about 30 team members. We're distributed all across the world. We've got someone up here in Alaska. We've got a good nucleation of team members in the United States. We have a large representation in Europe. We have a guy in Cyprus working on some of the computer technology that we're interested in. We have a student designer in India, and then we have someone way down in Australia. So this is really a sort of pan-national project. So what are the terms of reference? So this is what we're doing. So it's a 5-year theoretical design study to build an interstellar unmanned robotic probe that could potentially decelerate in the target system. And that's sort of one of the main differences from Daedalus, which was just a flyby mission. So flyby missions are, great. I mean, there are certain steps that we're going to have to take before we go to the stars. And, one of them is going to be precursor missions, perhaps to the Oort cloud, to the Kuiper belt, to 1,000 astronomical units, to 10,000 astronomical units. Possibly the first interstellar mission, possibly it'll be a flyby. Ultimately, what we're going to do is slow down, though, because if you think about a flyby mission traveling at about 10% the speed of light, it's going to whiz past Jupiter in about 3 seconds. It's going to whiz through that solar system incredibly rapidly. And by the time we reach the stage where we could launch an interstellar probe, 50, 100, 200 years from now, I'm not going to try and predict things, but it's very likely that we will have telescopic technology here on Earth or on the Moon that would be able to acquire as much data as a rapid flyby of the target system. So what we really want to do with Icarus is rendezvous, so interstellar rendezvous mission. So here is really sort of the foundations of our project, what we're attempting to do. We want to design an unmanned probe that's capable of delivering useful scientific information about the target star and hopefully any associated bodies around that target star. And I think we're in an incredibly exciting period now. I mean, I read an article recently, we've discovered something like 760 exoplanets, and so it's really getting more and more exciting. We're starting to realize that the galaxy is rich with planets, and that, what's the next step? Well, maybe there are some out there that are Earth-like, that are in the habitable zone. What can we learn about them? So that's one of the things we're very interested in. We want to use current or near-term technology. I mean, we want this to be a credible design study. I mean, like all of you, I'm very excited by some of the stuff we're seeing on the edges of theoretical physics now. But, until we sort of see some experimental evidence, I mean, for FTL, I mean, we've got the argument going on now with the neutrinos, but we want to use stuff that we know works that's at a reasonably mature TRL level. 2 or 3 perhaps, but something that we can progressively mature. And stuff like warp drives and wormholes don't even exist on the TRL level naturally. We want to reach the destination in a timescale not exceeding a century. Now, Daedalus actually had a stricter timescale. I mean, they were going to reach banana star in about 57 years. We've relaxed that a little bit, and I think that makes our mission a little bit easier. There's a relationship. So we want to allow for a variety of target stars because every month almost it seems like we're discovering new planets. So during this study, we don't want to fixate on Alpha Centauri or Epsilon Eridani too early on in the study in case we discover something more interesting at 6 or 7 like this, for example. And like I said, we want to design a craft that has some deceleration in the target system, preferably a full rendezvous, and that's sort of an ongoing debate within the team. This is how we've really split up the research modules. We've demarcated the project into 20 research areas that we think are the salient features that should be studied for an interstellar probe. So for example, we have someone studying the astronomical target, where we want to go. We have someone, we have primary propulsion, secondary propulsion. What kind of fuels are we going to use? What kind of power systems? What's the communications going to be? We're very excited by the work of Claudio and the focal research. I mean, this is something one of our guys is actively looking at. Navigation and guidance, and so on and so forth. What kind of science are we going to do when we get there? And we've assigned module leads to each of those modules, and those module leads have a team working underneath them. And what we've done is sort of, we've given ourselves a number of trade studies that are really educating the team up to the level where we can, comfortably down select in terms of the design of the probe. So like I said, this was inspired by Daedalus, and Daedalus was a huge, huge spacecraft. You can see this Adrian Mann image here. He's one of the artists on our team. He does absolutely phenomenal work. And you can see the Daedalus next to the Saturn V. So the Daedalus was about 55,000 tons. It was the size of a Nimitz aircraft carrier. It was a huge beast. It was designed, like I said, by the British Interplanetary Society. The propulsion system, and I'm going to gravitate towards talking about propulsion just because that's my area of interest, even though the problem is far more vast. So we used, Daedalus used a pulse fusion engine, which I'll talk about if there's enough time. The fuel was deuterium helium-3. Helium-3 is obviously very, very rare. It's not at all abundant on Earth. There is some quantities on the Moon, but evidence indicates that it's going to be very difficult to mine it in sufficient quantities. And the Daedalus team actually chose to mine from Jupiter, because that's where helium-3 occurs in abundance. Target was Barnard's star, because at the time, in the 70s, they believed there was a planetary system. The evidence that they had, we now know to be incorrect. There may actually be a planetary system there, but the evidence that they use has been sort of disproven. And what the final study involved was about 20 research papers that ultimately demonstrated that interstellar travel is or was possible with credible extrapolations of 1970s technology. So a very exciting sort of hallmark study. So our project, Project Icarus, has a fourfold purpose. We're not just designing an interstellar probe. One of the primary things we want to do is motivate the next generation of interstellar scientists. We've been inspired by some of the big names, like Rob Forward, for example, and some of the other big names in the field. But what we want to do is get the younger generation interested, and as custodians of that dream, we need to keep that interest alive for generations. We also want to generate greater interest in the real-term prospects for interstellar research missions. Like I said, it's our responsibility to get that message out there, to market what we're interested in doing. I mean, marketing is almost an ugly word. For physicists and engineers and scientists, we want to just do our research, but we have to sell what we're doing to get support for it. The third purpose is what I alluded to, the actual design of an interstellar probe, and four, to provide an assessment of the maturity of fusion-based propulsion systems. So Project Icarus, we had, there are a lot of options available to us, but to provide continuity with Daedalus, we chose to stick with fusion. So the origins of the project, this is on Lambeth Road in London, the headquarters of the British Interplanetary Society. We've been there a few times, I'm sure some of you have visited the headquarters. So really the founder of Project Icarus was Kelvin Long, and he got chatting with Mark Millis in 2008, talked about the idea of doing a successor study to Project Daedalus, and sort of got the thumbs up from Mark. He also approached the original Daedalus team and proposed the idea, who also gave him the thumbs up. And then I joined the team sort of a few months after he began that as co-founder, and then we've sort of been growing from there. So we launched the project on 30th of September 2009. So, I think one of the important outputs of a team is, we have to demonstrate that we're actually doing real scientific research. We're not just sort of like a little club sending each other emails. Wouldn't it be cool if we go to the stars? And, we're actually we're actually publishing papers. So here are some recent research papers that have passed through peer review or in the progress of being published. And also some of our output, we do a lot of blogging, a lot of articles to Discovery Space News, for example. So it's all sort of part of our mission. So a couple of years into the project, we started realizing that, hey, we need to get things a little bit more formal. We've got this great inertia, we have a lot of gravitas. Let's form a non-profit foundation and sort of start building from there. So we formed Icarus Interstellar, which was founded in March of 2011. And here's our mission statement. It essentially says that we want to accomplish interstellar flight by the year 2100. So we've given ourselves 89 years, so plenty of time to hopefully realize the ambition of an interstellar flight. And we say we're going to accomplish this by researching and developing the science and technologies that will make interstellar flight a reality, igniting the public's interest and engaging with everyone who's willing to invest in the program. So this is the team as it stands. So we've got a core design team of just over 20 people. About half have PhDs. Like I said, we're distributed all across the globe. We're fortunate to have a number of consultants on the team. We've got Vince Cerf, who's the Vice President of Google, who we're very proud to have his name associated with the project. We're incredibly happy to have Greg Matloff on the team, Paul Gilster on the team. So we've got this real great team of consultants who sort of help guide us and tell us when we're going up the wrong path, for example. And also we're getting more and more active with engaging the student community as well. So at the moment we just have 3 student designers. We define a student designer as someone who hasn't yet got their degree, undergraduate degree. So we think it's important to engage with the younger generation. And this is the way that we've organised the organisation. So we have the board of directors, And then we've broken things down. We have a research committee, under which Project Icarus, which I sort of described in a little bit of detail earlier, Project Icarus falls underneath that. And we have a number of other projects going. For example, Project Forward, which is a beamed energy propulsion program that we've just initiated. Project Persephone, which is going to be a study for a manned starship. Icarus, like I said, is unmanned, it's robotic. We also have the Public Outreach Committee. Like I said, we think it's important to engage with the public. So, you know, we have newsletters, we go to a lot of conferences, we publish things on Discovery Space News. And then business development as well. I mean, we're living in a new era here, you know, in the early 21st century. I mean, all we seem to hear on the news is that there's no money, there's no funding. You know, it's very depressing. And so what we're doing is saying, well, okay, if there's no money, let's go and find it ourselves. You know, let's figure out what people are interested in. And I mean, you know, if you think about it, if you can make 20 guys driving around a track over and over again for 5 hours interesting, which I'm talking NASCAR obviously, which generates billions of dollars each year. Surely, the research to build a probe to go to another star system, surely we can create some kind of business opportunity from that as well. So, you know, we want to take the initiative here and say, okay, if there's no money, we'll go find it ourselves. We also have an experimental research program going as well. For example, Project Helios and Project Bifrost, which are, Helios is based on attempting to create a working version, or a mock-up, if you like, of the Daedalus engine. And so that involves injecting pellets at high velocity into a reaction chamber and firing laser beams at them and igniting them. These won't actually be fusion pellets, these will be test pellets to demonstrate the process. And Project Bifrost is really work on emerging nuclear technologies, which I think is a critical step towards Interstellar. And if you think what the steps are going to be, it's very likely that we're going to start with fission propulsion, and then go to fission-fusion hybrids, and then go to fusion propulsion, and maybe even fusion hybrids, for example, antimatter catalyzed fusion systems. Maybe one day we'll have full antimatter systems, I don't know. So, we've only got about 5 minutes left, but yeah, there are lots of different classes of starships. So, for example, we can take advantage, we can overcome or circumvent the rocket equation by utilizing the fact that we know that photons carry momentum and can impart thrust. And so I'm sure Dr. Matlock is going to give you more detail on solar sails, and he might correct my numbers here, but solar sails potentially exit the solar system at a few tens of AUs per year, which isn't going to get us to the stars on timescales of a human lifetime. Beamed energy is another possibility. And what you actually do is beam a collimated channel of electromagnetic energy, laser energy, or more economically microwave energy. And we have someone working on this within Icarus Interstellar, Jim Benford, who's been an expert in the field for a number of years now, so we're privileged to have him on the team. Again, terawatt type energies to come up with sort of speeds on the order of 10% the speed of light. More energy than human civilization creates per year. So very ambitious, but within the known laws of physics, nothing new. Nuclear rockets, which can be split into fission and fusion. I mean, we had a working nuclear rocket with the NERVA program back in the 70s, nuclear engine for rocket vehicle application. It was designated as being flight worthy, I believe in the late 1960s, 69. Yeah, the program was shut for economical reasons, but we have nuclear rockets. And of course, another possibility, another class of vehicle are antimatter rockets. Dirac in the 1920s discovered as a solution to the relativistic Schrödinger equation that there were a type of mirror particle or antiparticles, and so for all known particles there can exist an equivalent antiparticle. So for electrons there are anti-electrons, or what we call positrons. For quarks we have antiquarks. And so an antimatter rocket would be ideal, but as was discussed earlier, at the moment antimatter is created in very, very small quantities, and it's very difficult to contain it for any large amount of time. So I'm going to wrap things up here. Orion was a very exciting class of starship, which Les talked about, and Daedalus, again, which was a very exciting class of starship. I'm not going to go into the details because we're down to about the last 30 seconds. So let's skip this. I don't want to go over time. So let me leave you with a very nice quote. So I said that all of these interstellar projects are going to be very, very difficult to do. I mean, we're going to need sails the size of Texas, people say. We're going to need Nimitz aircraft carrier size starships to get to the stars. But Anthony Marston, Project Daedalus, he said if all of this seems like an incredible undertaking, but if we are to tackle the problem on the astronomical scale, then we must attempt to visualize solutions to suit. Thank you very much, everyone.
We've got about 5 minutes for questions.
Okay, questions in the audience? Well, I have a prediction it's going to be a difficult one.
No, I don't think so. In Orlando, I had a discussion with one of the other consultants on the team, Jim French, who's probably the world's foremost rocket engineer alive today. And Jim mentioned that one problem with the Daedalus Icarus motor engine at this point is you have these little bursts going off 200 times a second or so of fusion pellets.
Yeah.
And the backflow from that might create, or he said will almost certainly create, very strange acoustics in the bell. Have you seen anything further about that in the last month?
We haven't done a dedicated study of the harmonics of the Daedalus engine, but what I will say is that we're not actually at the stage where we're down selecting. Now there are about 14 or 15 different ways you can accomplish fusion, ICF being one of them, and ICF has about 4 or 5 different categories. You know, shock ignition, you're using these Horons and stuff, and of course we've got magnetic confinement fusion, colliding beams, we've got all these different types, 14 or 15 different types of ways of accomplishing fusion. And what we would like to do over the coming 12 months or so is start the selection criteria, start that down select. And you know, what we've got is a relatively young and immature team who are trying to understand the landscape. And so, you know, we're trying to understand what are the different fusion options, and then how do we start, you know, knocking things off. Okay, we don't want MCF perhaps because there's too much mass in terms of the shielding required and so forth. So until we decide, yes, we're going to go ICF, if we make that decision that we're going to sort of go the ICF route, then that will probably be the stage when we're going to study the harmonics of the engine.
Okay.
But thank you. Paul.
Rich, deceleration is a huge problem.
Yes.
Given what we know about what it would take in terms of fuel to slow down in your destination system. Would you comment on what kinds of deceleration options are currently being looked at, and are you looking at something like a mag sail for possible deceleration?
That's a really good question. So as Paul said, the problem gets exponentially harder. It's not twice as hard to decelerate a probe. It's exponentially harder. So we're looking at a number of options for how we will actually engage in that rendezvous mission. So one of the simplest things we can do is just turn the engine around and decelerate, for example. Now the Daedalus study had a top delta V of about 12% the speed of light, and they did all that for traveling at a plus 12% the speed of light. But if you turned that into a 6% speed of light one way and then decelerated for another delta V of 60% to do the rendezvous, then you would still be able to reach a closed star system like Alpha Centauri within our 100-year time frame. But there are more exotic ideas out there. I mean, we can take advantage of some of the surrounding material. For example, there are mag sails. These are devices that interact with the local interstellar medium, for example, that will in effect create a magnetic drag, which may be able to slow us down. And there are about 20 or so ideas that are currently floating around the team. So it may not be a simple case of just turning the engine around and decelerating, but a case of doing something more exotic, like utilizing mag sails.
I think we need to break for our next speaker, our last speaker before lunch. So thank you very much.